Okay, finishing up derivative set number 3, Extrema. This is going to be part 2 of this set. Okay, so we're going to start off with interpreting the first derivative. So we know that if the first derivative is positive, the original function is increasing. If it's negative, the original function is decreasing. In order for you to have a local max or relative max, the derivative must go from positive to negative. In order to have a local min, it goes from negative to positive. Remember, if you're looking for these things, you're going to plug into your derivative, not your original function. Okay, so let's start with the first example. It says identify where the function's increasing or decreasing. So we're going to take our first derivative. So our first derivative is 4x cubed plus 12x squared. Now, they have a 4x in common, so 4x squared, so let's factor that out. And we're going to find our critical points. So our critical points are 0 and x is equal to -3. Now we're going to make our number line. Put our 0 and we'll put our -3 on the number line. So we're going to plug into our derivative. Remember, anything squared is always going to be positive, so that's not going to make a difference. So -4 plus 3 is a negative. Plug in a -2, should be positive, and plug in like a 1, should be positive. So this thing is going to be increasing from -3 to 0 in union with 0 to infinity. It's going to be decreasing from -infinity to -3. Okay, and that's how we answer that question. So if you notice, you'd have a local min right here, but the question's not asking that, so we're not going to find it. Okay, next example. It says you want to find increasing, decreasing in all local extrema. Okay, so take our first derivative, we get 6x squared minus 18x minus 60. Okay, it looks like they have a 6 in common, so we're going to factor out a 6. And we're going to factors of 10 are going to be -5 and +2. So we get x is equal to 5 and x is equal to a -2. So we're going to put those two things on our number line. And we're going to plug into our derivative. Okay, so plug in -3. -3 minus 5 is a negative. -3 plus 2 is a negative. Negative times a negative is a positive. Plug in a 0, you should get negative. And plug in a 6, you should get a positive. Positive to negative is a max. Negative to positive is a min. So this thing's going to be increasing from -infinity to -2 in union with 5 to infinity. It's going to be decreasing from -2 to 5. You're going to have a local max at x is equal to a -2, and you're going to have a local min at x is equal to 5. On this one, it gives us the derivative, so all we have to do is set it equal to 0, find our critical points, and plug into our number line. So they have a 12x in common. So that's how it factors. So we get x is equal to 0 and x is equal to 3. So we're going to plug into our number line. Okay. Now, so let's plug in like a -1. Negative times a negative is a positive. Plug in a 1, should be negative. Plug in a 4, should come out to be positive. So you'll have a local max at 0 and a local min at x is equal to 3. Now remember, relative is the same thing as local, so don't get confused by that language. Okay, last problem on this paper. So once again, you're given the derivative, and we want to find the extrema. So what we're going to do is set each parentheses equal to 0. So you get x is equal to 1, x is equal to -2, and x is equal to 3. And we're going to make our little number line. Okay, so anything squared is always positive. So we're not going to even plug in to these two things. So if we plug in -3, okay, so -3 minus 3 is a negative. Plug in a 0. 0 minus 3 is a negative. Plug in a 2. 2 minus 3 is a negative. Plug in a 4. You get a positive. Okay, so you have a local min at x is equal to 3. Okay, and those are common multiple choice questions. Okay, let's go on to our second derivative. Now our second derivative tells us about concavity. Okay, if your second derivative is positive, it's concave up. If your second derivative is negative, it's concave down. An inflection point is where there's some sort of change in concavity. You can't assume that just because the second derivative is equal to 0 that you have some sort of inflection points. Okay, so it's pretty much the same exact steps as what we just did on the first derivative. Okay, but we're looking for inflection points in concavity. Okay, so we're going to take our first derivative. So we get 4x cubed plus 24x squared minus 144x. Our second derivative is going to be 12x squared plus 48x minus 144. Now, they all seem to have a 12 in common, so let's factor out 12. And this is going to break down into x plus 6 and an x minus 2. So on our number line, we're going to have x is equal to a -6 and x is equal to 2 for your possible inflection points. Okay, so we're going to plug in a -7. -7 plus 6 is a negative, times negative is a positive, 0, that's going to be a negative, and plug in a 3. Should be a positive. Okay, so it's going to be concave down in the middle. So it's concave down from -6 to 2. Okay, next example, it says find the x-coordinate of the inflection point. Okay, remember inflection points have to change concavity. So we're going to take our first derivative. We get 3x squared minus 30x plus 33. And the second derivative is going to be 6x minus 30. We set that equal to 0. We get x is equal to 5. Now, from there, we're going to do our number line. Put our 5 on there. So we're going to plug into our second derivative for concavity. So if I plug in a 0, get negative, and a 6, I get positive. So we have an inflection point. So we got an inflection point at x is equal to 5. Find the points of inflection and intervals of concavity for this function right here. So we're going to take our first derivative. E4 minus x squared. So the derivative e is e to the u du. And then for our second derivative, we're going to have a product rule. Okay, so we're going to write the first term. Derivative of the second term is -2 plus. Write the second term, derivative of the first term, like that. Okay, so like we've done in the previous examples through derivatives, we have e's. It's a lot easier if you factor out the e term. Now remember, e's will never equal to 0. So when I cancel that, I'm going to get -2, and this is going to be a 4x squared. And this will be the portion that we set equal to 0. So negative 2 plus 4x squared is equal to 0. So we get 4x squared is equal to 2. So x should equal to plus or minus the square root of 1/2. Now we're going to make our little number line. Okay. Now, pick numbers. I'd pick like a -1. So plugging in -1 squared is a positive. So 4 minus 2 is a positive. Plug in a 0, comes out to be negative. And then plug in +1, should also be positive. So this thing is going to be concave up from -infinity to negative square root of 1/2 in union with square root of 1/2 to infinity. It's going to be concave down from negative square root of 1/2 to square root of 1/2. And you have inflection points because it changes concavity at both of those points. So you have inflection points at x is equal to plus or minus square root of 1/2. Okay? And that's how we completely answer that question. Okay, last example problem. It says locate the points of inflection given the second derivative. Okay, so what we're going to do is we're going to set each one of those parentheses equal to 0. So we get x is equal to 5, x is equal to 1, and x is equal to a -2. And we're going to put those all on our number line. Okay, we're going to plug in a -3. Okay, so a -3 minus 5 is a negative, so that comes out to be a positive. -3 plus 2 is a -1, so this should come out to be negative. Plug in a 0. Negative, positive. So that should be a positive. Plug in a 2. Negative, positive, positive. And I'm going to plug in a 6. Positive. So everything's positive there. So your inflection points should occur at x is equal to a -2, x is equal to 1, and x is equal to 5. They're all inflection points. Now, you cannot assume that those are inflection points unless it changes sign. It's very, very important that you do that. Okay, I'm just confirming my work. Just give me a sec. Make sure I didn't mess anything up. Okay, yep, that's right. Okay, next page. Putting everything together. So when we put everything together, we're going to be finding all the stuff we just previously found, including the domain. So your domain in this case is going to be -infinity to +infinity. It's a polynomial function. There aren't any asymptotes because it's not a fraction. Okay, now we're going to start off by finding our first derivative. Okay, they have a 3 in common, so let's factor that out. Okay, factors of 15. Looks like that. And then we're going to say x is equal to -5 and x is equal to 3. That goes on our first number line. Okay, so we're going to plug in a -6. Negative times a negative is a positive. Plug in a 0. Plug in a 4. Okay, so we have a max. We have a min. Okay, so this thing is going to be increasing from -infinity to -5 in union with 3 to infinity. It's going to be decreasing from -5 to 3. You get a local max. X is equal to -5. You get a local min at x is equal to 3. Okay, now let's do our second derivative. So the second derivative of this thing is going to be 6x plus 6. So we're going to set that equal to 0. We get x is equal to a negative 1. Do our little number line. So plug in negative 2, should be negative. Plug in a 0, it should be positive. Okay, so if we were to graph this, we have a max at negative 5, so something up here, a min at 3, and it's going to change concavity at negative 1. It's going to be concave down until it reaches here, then it switches to concave up. It should look like that. Something similar to that. Okay, next example. We're going to have some asymptotes. Domain of this one is going to be negative infinity to positive infinity. X cannot equal to a negative 3. Remember, vertical asymptotes, the bottom cannot equal to 0. It says, let's find our asymptotes. Vertical asymptote is x is equal to negative 3. You're going to have a horizontal asymptote at y is equal to 2, or the end behavior. You've seen some of that on previous sets. The end behavior is going to be the limit as it goes to infinity. Okay, so start by taking our first derivative. So we're going to write the bottom, derivative the top, minus write the top, derivative the bottom, all over the bottom squared. Okay, so we get 2x plus 6 and minus 2x from there. Combine your like terms, so you should get 6 over x plus 3 quantity squared. Now, the top of this fraction will never equal to 0, and the bottom of the fraction will be equal to 0. So your only critical point is going to be x is equal to negative 3. So we'll go do our little number line. Now, since x is equal to a negative 3 is a vertical asymptote, I'm going to draw a little dashed line through it so I know it's an asymptote. It can't be a max or a min. Anything squared is always positive. Okay, 6 over a positive number is always positive. So this function is going to be increasing from negative infinity to negative 3 in union with negative 3 to infinity. Now, go to our second derivative. I would do a nice little rewrite at 6 times x plus 3 to the negative 2 power. So when I go to do my second derivative, it's negative 12 x plus 3 to the negative 3 times 1. Okay, so our second derivative looks like that. Now, we're going to have the same issue to where the top doesn't equal to 0. So the only thing that we're going to have is where it's undefined is that x is equal to a negative 3. Okay. Now, if I was to plug in a negative 4, negative 4 plus 3 is a negative, and negative over a negative is a positive. Say I was going to plug in a 0. I get a negative. So what's going to happen is this thing is going to be concave up from negative infinity to negative 3, and it's going to be concave down from negative 3 to infinity. There are no inflection points because you can't have an inflection point on an asymptote. And if we wanted to take a little look at what the graph looks like, what we would do is we would plot our negative 3 like this and our horizontal asymptote like that. We know it's concave up, and this portion's concave down, but it's always increasing. So that's what your graph would look like. Okay, continuing this stuff. Now, when we're doing derivative graphs, interpreting the derivative graph is super, super important. So if you remember, what we did before is we labeled all of the zeros on the derivative graph as your critical points. Now we went from negative to positive. That doesn't change sign, and this is positive to negative. So I know I have a local max at x is equal to 5 because it goes from positive to negative. I have a local min at x is equal to a negative 7. Now, this doesn't change sign, so it's not a local max or a local min. This thing is increasing where we have positive y values. So this thing's going to be increasing from negative 7 to 5, okay, all the way out there. And it's going to be decreasing from negative infinity to negative 7 in union with 5 to infinity, okay? So that's negative y values. Now, if we're talking about inflection points occur at the hills and valleys. Okay, so we're gonna have inflection points at, it looks like x is equal to a negative 5.5, negative 2, and 3. This graph is going to be concave down where the slopes are negative, okay? So you have negative slopes from negative 5.5 to negative 2 in union with, looks like 3 to infinity. It's going to be concave up where the slopes are positive, so negative infinity to negative 5.5 in union with negative 2 to 3. Okay, and so that's fully how you interpret the derivative graph. So we're going to kind of talk through this one. I'm not going to write everything out. I don't know if I have room. I'll try and write it out. Okay, so our first step is to identify our zeros, because that's going to be our maxes and mins. Okay, so positive to negative is a max. Negative to positive is a min. And positive to negative is a max. So it looks like we have a max, I'd say it's negative 4.25. And I have another max at 3. Okay, I have a min at negative 1. Okay, now I know I have positive y values going to be increasing the original function. So it's going to be increasing from negative infinity to negative 4.25 in union with negative 1 to 3. Okay, it's going to be decreasing where we have negative y values. So negative 4.25 to negative 1 and 3 to infinity. Okay, now if you wanted to say 3 to 9, that's fine. Just assume that the graph's just going to continue. Concavity and inflection points. So your inflection points are going to occur at the hills and the valleys. So I have an inflection point here, and here, and here. Okay, so I have inflection points at x is equal to negative 3, 1, and 7. Okay, and we'll just kind of cut that off over there. So this thing's going to be concave down where the slopes are negative. So it's going to be negative infinity to negative 3 and 1 to 7. It's going to be concave up where the slopes are positive. So your slopes are positive from negative 3 to 1 and 7 to infinity. Okay, it's super important that you learn how to do this because this is going to be super important whenever you start doing functions defined by integrals and free response. And if I had to bet money this year, it's going to be on this year's test. Okay, interpret the following graph of the second derivative. Okay, so the second derivative tells us inflection points. So if it changes from negative to positive y values, your inflection point would occur at 0. Okay, so you would have an inflection point at x is equal to 0. It's going to be concave down from negative infinity or negative infinity or negative 2, let's just say negative 2 to 0. And it's going to be concave up from 0 to 2. Okay, last two questions. It says, if f prime of x is, so this is going to be calculator work, so make sure your calculator's out and make sure you're in radians. Okay, so it says if f prime of x is given as that, find the local max. Okay, so we know that local maxes go from positive to negative. I'm going to zoom in just a little bit. So I'm going to put this into y equals square root of x to the 4th plus 1 plus x cubed minus 3x. And I'm going to graph it. So I'm looking where it goes from positive to negative. And if I look at it, zoom in just a little more. I can't really zoom in, sorry. It's right here. So we do second calc, 0. And we're going to go above and below. And I got 0.350. Okay. Given the derivative, identify all the intervals in which the graph is concave down. Okay, I can tell concave down by the second derivative. Okay, so there's two choices. You can either take the second derivative and look for negative y values, or you can look at the first derivative and figure out where they have negative slopes. Okay, might be easier to take the second derivative on this one, up to you. So derivative e is either u du. Minus 4x. Okay, so I'm going to put that in my calculator and I'm going to locate the zeros. And I'm just going to put another set of parentheses just to be careful. Okay, it's concave down where we have negative y values. Okay, so it looks like we're going to have negative y values. Here, let me put this down just a little bit. So it looks like we're going to have negative y values in this region right here and this region right here. Okay, so use your calculator, second calc, 0. So it's going to be negative infinity to negative 1 in union with looks like 0 to 1. So we're going to find our zeros. Oops, sorry. I messed up. So we're looking for concave down, so 0 to 1. Yeah, 0 to 1. Okay, so once again, what I did is I did second calc. 0, and I found these zeros right here. So I'm looking where it's negative y values. So then it'll go positive from -1 to 0, and then I'm going to find the other 0, which comes out to be 1. Okay, so hopefully this helps you go through the calculator a little bit and remember how to do these types of questions. When you have a calculator and you use your zeros, the alternative method, I'll just talk through this real quick, is if I take the derivative function, okay, don't forget the -2, and I graph it. Now, I know that we're going to have, it's going to be concave down where the slopes are negative. So the slopes are negative from here to here and from here to here. So if you want to find these two mins right here and that max, that's fine with me. You can do second calc max, second calc min, and go about it that way. Okay? So hopefully this was helpful, and you should be good to go to do derivative set number 3 over Extrema. Have a good night.